Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. And I am very happy to have Gabriel Grell with us today. Hello, Gabriel.
Hi, how's it going, Frank?
I am doing awesome on this September 19th of 2024 as we record this. And I'm in Phoenix, and we are actually finally getting our fall weather. Today was the first day I walked outside and went, it's fall. So it was kind of cool. And Gabriel, where are you at? What's
I'm in Greenbelt, Maryland, so I am a postdoctoral fellow at the NASA Goddard Space Flight Center.
very
Actually, just started this role as of last week, so
Oh,
still
so
getting getting my feet wet back.
so you just got your PhD?
Yep, I defended in late July, then took all of August off, and now I'm getting back into the swing of things.
Oh, Dr. Grell, congratulations.
Thank you.
Let's see. That's pretty awesome. Let's see. It's on the East Coast, so are the leaves starting to change a little bit? Are we starting to
Yeah,
get?
the leaves are turning orange, but still waiting on the temperature to drop a little bit.
Yeah, yeah.
Yeah,
Very cool. Very cool.
that's classic Maryland weather for you.
Indeed. And Gabriel, what do you like to do for research?
So I specialize in the different branches of X-ray astrophysics. So I have done theoretical, laboratory, and observational astrophysics, and I've gone back and forth between how the streamline process works. So we use theoretical models to analyze what we see from space, but in order to make sure that our theoretical models are up to snuff, we also do experimental work to make sure that our theoretical models are properly benchmarked.
Very nice. You're a proverbial triple threat there. Well, instrumentation, experiment.
Yep, the whole trifecta.
There you go, the whole ball of wax. And let's go. That'll bring us to this very lovely APJ article. It is open access. It's the open access era, people. You can go grab a copy for free. Go get one. Laboratory benchmark of n greater than equal to 4, dielectronic recombination satellites of iron, XVII, and Gabriel, take us away.
Got it. Well, before I start, I want to thank my co-authors here, especially my thesis advisor, Maurice Leutenegger, and another co-advisor of mine, Chintan Shah, as well as Pedro Amaro and Jose Crespo Lopez Ortia, who all have helped me both throughout my PhD and also when running different experiments, which I'll get into very soon in the article.
Great shout out. Great shout out.
Yep.
Okay, let's
Yep.
roll.
So as I alluded to before, my research specializes in analyzing the X-ray spectra of hot astrophysical plasmas, specifically looking at the spectra of highly charged ions, which are the predominant form in which most elements appear as in the visible universe. And the primary ion that's been my chief research focus has been neon-like iron, or iron 17,
Okay.
which is the dominant iron ion over a very broad megakelvin, the temperature range.
Okay.
So these transitions provide very useful diagnostics of the physical conditions in hot astrophysical plasmas, and this includes electron temperature, density, velocity, turbulence, etc.
Cool.
And so decades of measurements have attempted to measure the wavelengths, cross sections, and intensity ratios of these transitions because they're so prominent in different astrophysical objects. But there exists a roadblock, and that is that there have been significant discrepancies found between the experimental, theoretical, and observational calculations of iron 17 cross sections, specifically the 3D to 2P and 3S to 2P transitions.
Okay.
So, because of these discrepancies, and because of the potential diagnostic utility of these transitions, astrophysicists have attempted to try to solve these discrepancies through different means, specifically looking at the key line formation processes that produce iron 17 in these objects. And this includes dielectronic recombination,
Okay.
which is the dominant recombination process for iron 17.
Okay.
And to explain dielectronic recombination, it's a simultaneous process where a bound electron is excited to a higher electron level, while a free electron is simultaneously captured at the same time.
Very cool.
This creates a doubly excited intermediate state.
Yes.
And then this intermediate state that has two possible final states. Either one, it spontaneously autoionizes, which
Yes.
results in resonant excitation,
Okay.
or one of those doubly bound electrons recombines, thus completing recombination, hence the name dielectronic recombination.
Very cool. Thank you for that. That was a great explanation. Okay.
Yep. So DR is responsible for the production of satellite lines that are adjacent to the main resonance 3D to 2B transition lines. And so understanding whether the contributions of DR to the iron 17 line formation, whether it's causing or has something to do with the model data discrepancy, is essential for trying to further improve the plasma diagnostics at our disposal. And this is important because the with future present and future X-ray spectrometers such as XVII, Athena, the line emission mapper, etc., on the horizon, it is important to have better constraints on the cross sections of these transitions, because the more spectra that we can see, the more that we can resolve, the more lines that have previously gone unanalyzed will start to pop up. So we want to make sure that our theory and experiment are converged so that we can further our understanding of whatever we see from space.
Cool. I'm with you.
Cool. So that brings me to this work in particular. So in this work, we use a software package called the Flexible Atomic Code to calculate the line emission cross sections for the three main line formation processes of iron 17, which are dielectronic recombination, direct excitation, and resonant excitation.
Okay.
With these configurations, which I'll get into soon. And then we benchmark these theoretical calculations using experimental cross sections in ions that were excited in a device called an electron beam ion trap, which I'll get into very shortly. Cool. So we benchmark our theoretical predictions with experimental data in order to try to further improve the constraints on the iron 17 cross sections. So
let me ask. Well, maybe you'll get into it. I'll let you get into it and then I'll ask a question. So go ahead. I'm good.
Oops. The light in my room is motion censored. 1 second.
Technology, it always works. It's wonderful.
Sorry about that.
There, it's all good. Now you're back.
Okay, cool. Okay, so starting with the experiment. So as I said before, we can benchmark our theoretical calculations using a device called an electron beam ion trap, which is a device that uses an electron beam focused with a strong magnetic field to ionize and trap highly charged ions. So I compare an EBIT to a particle accelerator in that we are taking advantage of electric and magnetic fields in order to produce particles that otherwise would only exist in the hottest plasmas in the universe.
Nice.
So as my advisor at the Max Planck Institute in Germany, Jose Crespo, said, we are taking advantage and harnessing the power of the stars by using these atoms.
Very cool.
So we made you.
Okay.
So yes, in this case, we made use of the flash EBIT at the Max Planck Institute for Nuclear Physics in Heidelberg to produce a population of iron 17 ions. So in this case, a molecular beam of iron pentacarbonyl, which is this oily yellow liquid, was injected into the EBIT using an injection system, and then ionized to higher charge states, in this case iron 17, by successive electron impact using the electron beam, and compressed to a sub-millimeter diameter using a 6 Tesla magnetic field.
Wow. Very nice.
The ions were then trapped radially by the negative space charge of the beam. So because it's a beam composed of electrons, it'll have a negative charge. And then electrostatically confined in the axial direction by potentials applied to the drift tubes that are within the center of the electron beam ion trap.
Okay.
Yep.
Cool. Very nice.
So for this particular experiment, we made use of a certain energy beam scan technique where we applied a charge breeding time where we do a ramp up and ramp down scan technique. So what I mean by that is that we ramp up the electron beam to 1150 EV, which is right below the ionization threshold for iron 17.
Okay.
Then we follow that with a ramp down to 300 EV, which is right below the ionization threshold for iron 16, or sodium-like iron. And by doing this, we effectively maximize the purity of iron 17 ions by suppressing any lower charge states that would possibly form.
Okay.
Yep. So, and while that's going on, we made sure that we maintained a constant electron density in the trap by syncing the electron beam current with the electron beam energy.
Mm-hmm.
Yep.
Yes. Okay, good. I'm with you.
Cool. So the produced X-ray intensity from this experiment was then collected using a silicon drift detector with a photon energy resolution of about 120 EV.
Nice.
Full width half max.
Here we go.
Yep. So then this particular experiment occurred in 2019. So the prominent publication that resulted from this work was Shaw et al. 2019, which focused on the line emission cross sections for the 3s to 2p and 3d to 2p channels of iron 17 ions. So, and now that brings me to my particular work here, where I'm focusing on the remainder of the channels produced from the experiment. So that, to allude back to the title, the n equals greater to and equal to 4 cross sections here.
Okay.
Yep.
Good. All right.
Cool.
We have complete. Good.
Yep. So that completes the experiment overview. Now that brings me to the theoretical cross section calculations. Okay. So we made use of the flexible atomic code, which is a software package that is able to calculate atomic structure for a highly charged ion. So we performed calculations for the channels of DR, resonant excitation, or RE for short, and direct electron impact excitation, or DE for short, with these configurations that you see here. So without going too much into the atomic physics, we basically wanted to make sure that all of the potential resonances that we produced in the experiment, we would also have in our theoretical predictions.
Nice. Good. Okay.
So with all these configurations, this led to having over 500,000 eigenstates. So in order to run this calculation, we made use of the NASA Discover supercluster in order to run a calculation of this, because if I ran this locally, it would probably take multiple days to do. So yes, we were able to do a full order configuration mixing calculation for these configurations.
Very cool. Very cool.
And we calculated the DR resonance strengths in the isolated resonance approximation. And in this approximation, the DR strength is shown by this equation, which, without breaking down every single element here, is a function of the integral of the DR cross section as a function of the free electron kinetic energy.
Yes.
Okay. Which, if you break down further, is a function of the auto ionization rate and radiative transition rate.
Very good. All right, I'm with you.
Cool. So that's our theoretical calculation overview.
Okay.
So now to get to the good part, which is data analysis and results. So before we can do the direct comparison, there are a few things we have to take care of. So first, we do a data calibration where we correct for different systematics that happened in the experiment.
Okay.
So one of which is correcting for the transmission of the carbon foil in front of the silicon drift detector, which shields the detector from UV light, but also partially blocks some X-ray radiation. So to correct for this, we calculated the transmission using optical constants from previous works, and then we included the uncertainty from this transmission also in our error budget.
Okay.
Then next, we corrected for the observed X-ray account by dividing by the square root of the electron beam energy, because as I alluded to in our experiment, in order to maintain a constant electron density, we adjusted the beam current in accordance with the electron beam energy. So we did the same thing with our observed X-ray counts.
Okay, good,
Yep.
good.
And then finally, we calculated a gain correction for the silicon detector energy scale using calculated centroid photon energies for both the fat calculated and flash measured resonances,
Yes.
and then fit a linear model to that.
Okay. Okay.
Cool. Okay, so that takes care of the calibration. And then that brings us to, before I talk about table 1, I want to flesh out both sections 4.2 and 4.3.
Okay.
So I'll kind of talk about both of these sections in parallel. So if you can scroll down to 4.2.
4.2.
Yep. So so I want to make a distinction between the absolute cross sections and then 4.3, the doubly convolved cross sections.
Yes, right here.
Okay.
Okay, good.
So when I mean absolute, I'm referring to the normalization and comparison of the theoretical cross sections that we calculate using the methodology from previous works. And then by doubly convolved, that is a new technique that previously was not used in this kind of analysis.
Okay.
So starting out with 4.2,
Cool. Okay.
So in order to make a direct comparison between the experimental counts and our theoretical cross sections, we must first normalize the experimental counts. So by doing this, we selected a singular central. Sorry, kind of lost my train of thought. So, yep. So, we selected a peak within the experimental data that we could trace to a single and strong resonance.
Okay.
And I'm sorry, I lost my train of thought there.
All good. It's all good.
Okay.
Take your time. It's all good.
So
we normalize the data to some peak in the spectrum.
Yeah. So
Okay.
we selected a single and strong resonance located at 412 eV electron beam energy. And we selected this particular peak because it has the simplest structure of all of the dielectronic recombination channels in the data set.
Yeah,
which makes its prediction theoretically more reliable.
Right.
So we calculated a normalization factor to then apply to the experimental counts so that we can have a direct comparison of our theoretical predictions and the experimental counts.
Good. I'm with you.
Yep. So this procedure was implemented by Shaw et al. 2019 for the n equals 3 manifold. So we did the same thing for the n equals 4, 5, and 6 manifolds as well. The one change being we had different ROI widths, region of interest widths, for each of these manifolds. So what we did was rescaled the normalization based on the relative fraction of the experimental counts captured in the ROI.
Okay.
Okay. So in doing so that's the absolute cross sections there. So so I want to briefly go down to the top panel of figure 2 to kind of
figure 2. Okay, let's go figure 2. There is
okay. So that is this is a comparison of the n equals 4 manifold for our theoretical cross sections compared to the normalized experimental data here. So as you can see here, we have comparisons for DR channels as well as the DE channels on the right side of the plot for between 1000 to 1100 EV. But as you can see here, you may notice that there appear to be some features missing in the theoretical data from 600 to 700 EV electron beam energy. So it turns out that these features aren't actually missing in the theoretical results. What's happening, to scroll back up to 4.2 and 4.3.
One question. So the red here is the theory.
Yep.
And what is the gray and black?
The black is the experimental.
And the gray?
The gray is the uncertainty band of the experimental data.
Cool. Okay, got it. That's pretty good. Okay, so we have a apparent discrepancy here, but not really. So going to go back up.
Okay, a little more.
A little more. Okay.
Okay, yeah. So this is happening because of the finite energy resolution of the detector from the experiment, which again was about 120 eV full width half max.
Yeah. Okay.
So when selecting an ROI on the experimental data, the resulting spectral histogram loses some flux from the resonances of interest, while gaining flux from features that we are trying to exclude.
Okay, got it.
And this effect becomes even more prominent at n is greater than or equal to 4, as the DR resonances start to very closely overlap along the photon energy axis.
Right, and so you get washed out because of your resolution. Okay.
Right. So just to showcase this more, if you could scroll down to the top panel of figure 1.
Sure. Let's go down to the top panel of figure 1, and there we go. Yay.
Okay, so this is the measured X-ray intensity from the experiment in dependence of both electron beam energy on the x-axis and the photon energy on the y-axis. So what you're seeing here is basically a 2D histogram contour plot where the energies are the bins and the intensities are the contour values. And the labeled features here are the different contributions from DR, RE, and DE for different levels of the manifold.
Nice.
So when I'm talking about taking an ROI, what I mean is that we're taking a cut, basically imagine we're taking a square cut of these features in order to then project the cross sections from the contributions here.
Okay.
So it's, as you can see, because of the resolution along the y-axis, it's very difficult to try to single out a particular feature without another feature bleeding in to the box.
Right. So that was a 120 EV.
Yeah.
Yeah. Okay.
Yeah.
Sure.
So that's why in the experimental experimental cross section that you saw in figure 2, there are some features that are actually bleeding in to the ROI, whereas you don't see that in the absolute theoretical. So,
right. Okay.
So with that in mind, that brings me to section 4.3.
Okay. Yeah. 4.3.
Where
back up. 4.
Where we now implement a doubly convolved approach to combating this.
Yes.
Okay. So to reproduce the effect of the finite resolution, we employed a double convolution approach. So in the absolute section, we actually are broadening the theoretical cross sections only on the electron beam energy axis, so the x-axis, to account for its Gaussian distribution. But in now the doubly convolved approach, we will now apply Gaussian broadening along the photon energy axis to match the finite detector resolution from the SDD.
Yes. Good.
So in doing so, you can kind of think of it as the blur filter on a camera, where we are now broadening along the y-axis to match the experimental response function.
Very cool. And that's the double part. Okay.
Yeah, exactly. So to briefly just put this in mathematical terms, that's equation 2. We effectively convolve the theoretical cross sections with Gaussian broadening along both the electron beam energy spread and the photon detector resolution.
Yes. Okay. Well, other way around, X and Y. Yep.
Cool. So by convolving the theoretical cross sections through the detector response before applying the ROI cut, we are able to then get better fidelity for the comparison between theory and experiment.
Okay. Awesome.
Cool. So additionally, we also use this approach to separate the contributions from each particular DR resonance individually in order to observe the degree of blending within the spectral features.
Okay.
Which I'll be able to showcase even better in figures 3 and 4. But before we get to that, I want to show the bottom panel of figure 1 now to get a visual sense of what we're doing here.
Okay, so there's our original, and here is our.
So now, by matching both the electron beam energy spread from the EBIT along the x-axis and the photon energy resolution along the y-axis, we now have a direct comparison of our of our doubly convolved theory with the experimental results. So
Very
as you can see, all of the contributions that are visible in the experimental are now also visible in our theoretical results.
Yes, yes, yes. Let's just do a little global between these two so we see them both at once.
Yep.
Yeah, very good.
Cool.
Sharpens that up considerably.
Yep.
Okay.
So now we can do a direct comparison for the cross sections now. So let's go one by one. So down to figure 2 now.
Okay. And we saw this one. So let's do a global and get them both in there.
Yep. So as you can see, we had pretty excellent agreement between the DR and DE channels in the absolute. But again, those features from 600 to 700 electron beam energy were missing. But if you go down to the bottom panel now, not only do we get even better agreement for the channels in the doubly convolved, those previously missing features are now very much visible and in agreement with the experimental data.
Beautiful, beautiful.
So that's for the n. Again, that's for the n=4 manifold. And now to get Yep.
Yeah, cool.
And now to showcase the n=5 and 6, we can go down to the next page, figures 3 and 4.
Okay, 5 and 6. So let's do figure 3 first. Or we can cover them both if you want at the same time, up to you.
Yeah, we can kind of go over them in parallel. So the top again are the absolute cross sections, where we're not doing any broadening along the y-axis. So as you can see here, it appears that the experimental data is much higher than the theoretical cross section. But what we understand now is that the higher estimation is due to other DR resonances that are bleeding into the ROI. So now I'll direct your attention to the bottom plot here, which shows the red is the sum of all the DR resonances, the theoretical resonances. And I have in the different dash curve the individual contributions from each of the DR resonances that are bleeding in. So in this case, we're looking at n=5. So the blue dash curve is a direct comparison of the resonances in question. And then the green, yellow, and purple are all of the outside resonances that are bleeding in to the box. So because we can now visualize this, we can take a contamination fraction estimation to which I'll get into in a sec, into our calculations for resonance strengths and rate coefficients, which I'll discuss in a bit for the results in tables 1 and 2. But this goes to show that by implementing this method now, we have a more direct comparison between theory and experiment, and we can then get a better gauge of the level of overlap between the resonances that is occurring. So the exact same thing in n=6. So previously, we think that there's a bunch of features missing here, and the experiment is way overestimated. The theoretical is way underestimating what's going on in the experiment, but in reality, it's just the considerable level of overlap between the resonances that it's occurring. So now by implementing the doubly convolved method again, we see the amount of overlap that's going on now. And in doing so, we can now calculate a contamination fraction to where we can then just singularly focus on the n=6 resonances in this case.
Beautiful. Okay.
Cool.
That works really well at double convolve.
Yep. So to go back up now, kind of back and forth, but let's go to section 4.4.
Rate coefficients.
Yep. So now to put this into more, mathematical, quantitative results now. So we tabulate both the experimental and absolute integrated resonance strength. So not the doubly convolved. We want because the absolute is more of the benchmark of the theoretical prediction, i.e., directly what FAC is spitting out, what we want to compare. So we calculate resonance strengths, which is the integrated cross sections basically over a range of electron beam energies. And we we integrated each n complex over their respective beam energies. And then, as I alluded to before, we estimated contamination fractions from our doubly convolved cross sections to correct for the blending that's occurring in the n=5 and n=6 calculations. And additionally, we also inferred rate coefficients from both the experiment and theoretical results.
Good.
Which are the cross sections integrated over a Maxwellian distribution.
Yes.
And these this parameter are, excuse me, these parameters are convenient for both spectral modeling and analyses of single and multi-temperature plasma models.
Yeah. Very cool.
So that brings me to tables 1 and 2.
Ultimately is what we
So
want.
we
Go to
start with
table
table. Yep, we go back to table 1.
Nice. Okay.
So for each individual channel, for each of these features, which I have labeled in figures 1 and the panels of figures 1, we're able to compare both the experiment and theoretical integrated cross sections. And as you can see, we find pretty reasonable agreements across the board, other than the L and O cross sections here. Yeah, I'll show those again in the cross section plots, but the
pretty good.
Sorry, just the
that's pretty good. Okay.
Yeah, so we aren't entirely sure why there is a bigger discrepancy for these, but the resonance strengths are so much smaller in comparison to the more prominent channels that we deem them inconsequential.
Okay.
Yep. So that's table 1, and then the rate coefficients in table 2.
Which is what you want. Let's do a little global out on this one.
Yep. We find also, again, very reasonable agreement within 2 sigma for everything but the LNO channel.
3,000. Okay.
But yes, so that flash and fact, those are between the theoretical and experimental. And additionally, we also were able to compare our results to those reported on the open ADAS AAS database. So these are published numbers from previous theoretical calculations, and we also find reasonable agreement with these between these reported numbers and our results.
And so just to be clear, open ADAS is strictly theoretical.
Yes.
Gotcha. Okay. Let's do one more here for my sake. Oh, pretty good. Pretty good. Yes. Nice. Very good.
So again, the only considerable discrepancy that we see is for the LNO channel. But again, these strengths are considerably weaker than the rest of the channels, so therefore not as useful.
Robust.
Yeah, that's right. Yes.
Okay. Very good.
So that takes care of our data results now. So we can scroll down to discussion now.
Okay. Here's our figure 1. Just cover that. There's our rate coefficient formula. Okay.
Yep. Oh, so to briefly showcase so figure 2.
Figure 2. Okay.
So yeah, the DRLNO channel here, you see the experiment is considerably.
Oh yeah.
Yeah, that's a pretty significant discrepancy that you see here. So that kind of is why you see the larger discrepancies manifest in the table results.
It's a little better, but still, yeah, they're just weak features.
Yeah.
Yeah. Okay, figure 2, figure 3 and 4 were n equals 5 and n equals 6, and on to discussion. Okay.
Yep. So I covered a lot of the discussion section already just by talking about the improvement between the absolute and doubly convolved. So yeah, previously previous features that were either underestimated or weren't visible prior to are now both visible and an excellent agreement in the doubly convolved approach.
Yes, that was really novel.
Very
cool. Very, very cool.
Yep. So again, we were able to effectively benchmark the FAC results by using the experimental results for these for the n equals 4, 5, and 6 manifolds. And in doing so, we're able to benchmark them also with the OpenADAS database results as well.
In about 2 sigma, that's pretty good. Very good. Awesome. Very good. So now it's all ready for people to put in their codes and do some modeling of whatever the astrophysical phenomena may be.
Yep. And again, if we're able to effectively resolve these features in future high resolution spectrometers such as Athena, then these kind of studies will become very important in terms of making sure that we have the good enough constraints in order to make astrophysical conclusions.
Very cool. Beautiful. Gabriel, I want to thank you so much for walking us through your very awesome article here.
Thanks, Frank.
Beautiful. Let's see. And you kind of touched on it there a little bit, so toward the end. So let me go there. So where do you think we go from here, given the published article? Is there new experimental machinery coming on that will get those weaker peaks better? Do we go on to other ionization stages of iron? Do we go to higher N? Just sort of, next steps. What do you think are the next steps we take on this?
Yeah, you said it. You said the first thing you said. So
okay.
So we can potentially improve our experimental results by making use of a detector with a better photon energy resolution. So in this case, one device that we can make use of almost immediately is a microcalorimeter, which basically is a temperature, which is a detector that will absorb X-ray photons and then measure the change in temperature from the absorption of the X-ray photon and get a much better a much higher resolution a much higher resolution compared to a silicon drift detector. So by rerunning this EBIT experiment with something like a microcalorimeter, we would be able to achieve much better energy resolution, and as a result, a much lower uncertainty, which would lead to better agreement and therefore even better constraints. So for the same potential future high resolution spectrometer missions, we would have even better results for comparison between observational and theoretical models.
Nice, very good. Do you have one of those machines at your local place, or?
Oh, sorry. Once again.
Gotta wave. It's mostly one of those things you gotta wave your arm. You gotta wave your arm every once in a while.
Yeah.
Trigger, right?
I'm a little far from the trigger.
So do you have one of those experimental facilities where you're at, or do you have to go to Germany to do those, or?
So it's funny you mentioned that. For half of 2022, I was actually interning at the Max Planck Institute in Germany to construct a miniature electron beam ion trap to eventually bring back to Goddard.
Nice.
So we're hopefully going to ship that back within the next year to run experiments. To run experiments like that here locally. And Goddard also has microcalorimeters as well. One calorimeter here was actually used to calibrate the XVII mission, the X-ray imaging and spectroscopy mission, which was just launched last year, and also makes use of a microcalorimeter. So
cool. Well, the future's looking bright here.
Yeah, for sure.
Yeah, it'll be really fun to see this develop over the next couple of years as you build your new instrument there. It'll be very exciting.
Yep, always something to get the new horizons to do to see.
All righty. Gabriel, thank you so much for walking us through your very lovely article again.
Thanks so much, Frank.
Sure. And I hope this made your laboratory astrophysics day a little bit better, everyone, and we will see you on the next one.
Yep. Bye-bye. See you soon.